Welcome to the survey of the elementary principles in classical mechanics. In part 2 of this series, we will discuss various exercises and applications of the theory that was previously presented. We will begin today with the problem of a disk rolling in a plane. The statement is as follows. A uniform thin disk rolls without slipping on a horizontal plane. A horizontal force is applied to the center of the disk and in a direction parallel to the plane of the disk. We are to derive Lagrange's equations and find the generalized force, and we are to discuss the motion if the force is not applied parallel to the plane of the disk. I will assume that the disk is of constant density ρ, radius a, and confined to the vertical plane. Its center is the origin of the coordinate system O', where I want y' to be the symmetry axis of the disk, z' is the vertical axis, and x' will always point in the forward direction towards which the disk is rolling. And these assumptions aren't really necessary, but we can consider that at time t equals 0, it is parallel with a fixed frame O. Now, in the general context of point B, the force is not parallel to the plane of the disk, so it is horizontal. It has two components, x' and y', and these components will result in a torque having three non-vanishing components in turn. Now, the x' component of the force generates the y' component of the torque. This rotates the disk about its symmetry axis, and as such it drives the rolling of the disk in the x' direction. So this is what drives the forward rolling of the disk. The y' component of the force is responsible for the x' and z' components of the torque. The x' component of the torque causes the disk to rotate about its horizontal diameter. So if this overcomes the static friction between the disk and the xy plane, the disk will simply collapse on its side. As for the z component of the torque, it causes the disk's rotation about its vertical diameter and changes its direction in the xy plane. Throughout, we assume that the disk is never allowed to slip. As such, this leads to a non-holonomic problem similar to that of example 3 discussed in this section about constraints. In the particular context of point A, the force being applied to the center of the disk has a single component, which is parallel to the plane of the disk. As such, the torque has a single component along the disk's symmetry axis, so the disk rolls along a fixed direction, and the relevant degree of freedom is its angle of rotation phi. We know that for a system of particles, the total kinetic energy T is the sum of two terms, one corresponding to the center of mass motion and the other to motion about the center of mass, as per equation 131. The former is given by the total mass of the disk divided by 2 times the square of the disk's velocity, which is just the radius a times the angular velocity phi dot. Now, to calculate the latter, we must first calculate the moment of inertia about the disk's symmetry axis. We will discuss this in greater detail when we will reach the topic of rigid body dynamics, but in this case it's really simple. So for a constant density, or for an arbitrary density for that matter, we just sum each mass element of the disk multiplied with the squared distance between that element and the axis of rotation. And for a constant density, this integral is really simple, and the result is the one given here, 1 over 2 times m times a squared, where m is just the constant density multiplying the surface area of the disk, which is just pi times the radius squared. Putting the two together, we obtain the expression of the kinetic energy here as 3 over 4 times m times the velocity squared, and then the partial derivatives with respect to the generalized coordinate and velocity are really simple. They're the ones given here, and provide this expression of the generalized force, which is also the single Lagrange equation of the system. The next problem regards the escape velocity. So the statement is as follows. The escape velocity of a particle on Earth is the minimum velocity required at Earth's surface in order that the particle can escape from Earth's gravitational field. Neglecting the resistance of the atmosphere, the system is conservative. From the conservation theorem for potential plus kinetic energy showed that the escape velocity for Earth, ignoring the presence of the Moon, is 11.2 kilometers per second. In order for a particle of mass m to escape the attractive gravitational field, where capital M is the mass of the Earth and g is Newton's gravitational constant, the minimum necessary amount of total energy is E equals 0. Therefore, on Earth's surface at a radius capital R, we have the following conditions that need to be fulfilled. So the total energy E is T plus V and it's equal to 0. Then T is just m over 2 times V squared. And the potential will be minus m times capital G and divided by capital R. So putting everything together, we obtain this equality, from which it follows immediately that the velocity needs to be equal with the square root of 2 times capital M times capital G over capital R. And if we introduce the numerical values of the involved constants, which are listed here, it follows immediately that the escape velocity is roughly 11.2 kilometers per second. And in the next problem, we are going to discuss jet propulsion. The statement is as follows. Rockets are propelled by the momentum reaction of the exhaust gases expelled from the tail. Since these gases arise from the reaction of the fuels carried in the rocket, the mass of the rocket is not constant but decreases as the fuel is expanded. Show that the equation of motion for a rocket projected vertically upward in a uniform gravitational field, neglecting atmospheric friction, is the following, where m is the mass of the rocket and v prime is the velocity of the escaping gases relative to the rocket. Integrate this equation to obtain v as a function of m, assuming a constant time rate of loss of mass. Show, for a rocket starting initially from rest, with v prime equal with 2.07 kilometers per second, and the mass loss per second equal to 1/60th of the initial mass, that in order to reach the escape velocity, the ratio of the weight of the fuel to the weight of the empty rocket must be almost 300. Newton's second law of motion at a given time t will read mass times acceleration has to be equal with the lift force experienced by the rocket plus the force of gravity, and all of these quantities will be time dependent in the given problem. This vector equation has a single direction of interest, which is the z direction. So we can write the corresponding scalar equation for that axis, which is given here. So it's m times a must be equal with f minus t, because f is pointing up, and f minus g, sorry, because f is pointing up and the force of gravity is pointing down. Now, when we ignite the rocket's engine, the rocket is losing mass, and as such, it is gaining negative momentum, which would imply that across the whole system, the center of mass is moving towards the direction in which mass is being lost. However, for the entire system, this would violate the law of conservation of momentum, since initially the center of mass was at rest. So in order for the center of mass to remain at rest, the momentum loss per unit time needs to be counterbalanced with an effective force that is driving the rocket up, such that for the entire system, which is the rocket plus the gases that have escaped from its tail, the center of mass remains at rest. Therefore, the effective force felt by the rocket is the one given here, so it's v prime, which is the uh, velocity of the gases escaping from the tail, times the time rate of time rate for the loss of mass, and it gets a minus sign in front because this quantity is negative. As the rocket is losing mass, I need to put another minus sign in front for this quantity to be positive. And as such, putting this in the above expression, we arrive at the equation that was suggested in the statement of the problem. Now, once we made it here, the acceleration can be written using the chain rule of derivation as the derivative of velocity with respect to mass, multiplying the time derivative of the mass. And we know, once again from the statement of the problem, that this time derivative needs to be equal to a constant multiplying the initial mass m0. So m0 is the mass of the empty rocket plus the total mass of the fuel. And this quantity delta is a constant that is negative. So it is implied that I have a minus sign contained in here. With these two expressions brought into equation 1 and dividing everything by the mass, we obtain the differential form here, which can be integrated right away to give the result here up to some integration constant. This constant is fixed from the initial condition, namely that when the rocket's fuel supply is full, so at the initial mass the velocity is 0, and using this condition I can obtain the final result, which is the one here, which gives the velocity of the rocket as a function of its mass, where once again m is the mass at a given time, m0 is the initial mass of the system, v prime is the velocity of the gases escaping from the rocket's tail, g is the gravitational acceleration, which is assumed to be constant, and delta is the constant uh, rate of mass loss per unit time. Now I can solve this equation for the condition that m reaches its minimal value, which is the mass of the empty rocket, and the result is here where I have written, so the variable m has become me, standing for empty, and m0 is the constant being equal to me, the mass of the empty rocket, plus mf, the total mass of the fuel. And this quantity is going to be equal with ve, which I will assume is the escape velocity. I want to use the condition of this being equal to the escape velocity in order to find the ratio of these two quantities. In order to solve the problem further, I will go by the assumption that me over mf is much smaller than 1. And with this assumption, I can neglect the term here. And within the argument of the logarithm, I can force a factor mf down here as a common factor, and then I can forget about the ratio in the brackets, which leads me immediately to the formula here, which I can easily solve for the ratio of mf to me and obtain finally the boxed result here, which once again keep in mind that the quantity delta appearing in the exponent is negative, so overall the sign here is positive, is a plus. Now I just need the numerical values of all of the involved parameters, and it turns out immediately that the ratio of fuel to the empty rocket is indeed almost 300. In particular, it is equal to 297. As an illustration, I have plotted the velocity in kilometers per second as a function of the system's mass in tons for the set of parameters listed here. So what you see in the figure is this equation for that particular set of parameters, and you can see that at the initial moment we are at rest, and then we begin to gain speed as the rocket loses mass, and the lighter the rocket gets, the faster it gains velocity up until it reaches the value of the escape velocity at once the fuel tanks are empty. Alright, all that being said, I will continue discussing the problems in the next video. I hope you found this one worth your time. I want to thank you very much for watching, and I will catch you later. Goodbye.